Hi there, everybody. This is Mr. Willis coming to you with more information about the wonderful world of chemistry. Today we are going to talk about chemical reactions, and specifically we are going to talk about double replacement reactions and some information about solubility. We'll also have an opportunity to review combustion reactions. All right, so let's jump right in. Today we are going to talk about how to classify things as a double replacement reaction and predict the products, and here's going to be our new topic, using the solubility table to determine if something will precipitate in a double reaction or not. And so that's going to be the big new idea. So in a double replacement reaction, remember that we start with two compounds, typically ionic, and that those ions then will switch partners to form two new compounds. And so you start with two compounds of one type and you switch. So your A, B, C, D, your A and your C, the two cations, will switch partners, and you'll end up then with A, D, and C, B. Here's an example, and in this case we have H2SO4, sulfuric acid, and sodium hydroxide, NaOH, and they switch to become sodium sulfate and water. This is actually a special subtype of double replacement reaction because it is an acid-base neutralization. We have the acid that starts with the H and will release some hydrogens. We have the base which ends in OH or hydroxide and will release those hydroxide ions, and your H plus from your acid and your OH minus from your hydroxide will form water molecules. So this is not only a double replacement but a special subtype known as an acid-base reaction or a neutralization reaction. But you can still see what happens is you end up with H2O and Na2SO4. So again, you start with a compound, and that yields a new compound and a new compounds. And so you down here we have a nice box that's covered by the ball hold still. Maybe it'll go away. But anyway, you end up with two new compounds being formed. Remember that the cation, or the positive ions, always come first in an ionic compound. So do not put the anions or the negative ions at the beginning of your compound. Always put your cations, your positives, first. Always start with the best foot forward, positives first. All right, and again, two compounds yield two compounds, which are new and different. Again, A, B, C, D goes to A, D, and C, B. This is an example of one which is not an acid base. We still have a base with the hydroxide, sodium hydroxide, but in this case, the sodium and the copper, and if you look, you can see that this is copper 2 because there's two chlorines were required instead of only one. If this had just been CuCl, we would have known that was copper 1, but since there's two chlorides, we know it's copper 2. And so then we'll end up with CuOH2 and NaCl. Again, I want you to notice that when you make your new compounds, you must reassess and recombine your elements, and so you have to redo the charges. And so you can't just assume that there will be two chlorines in your new compound. There's not in this case because it combines with sodium, which is a +1, so you need a -1 to go with it. And again, the hydroxide doesn't come across as a single anymore. There have to be two of them to pair with the copper. However, remember, we don't only have one molecule of each compound reacting. We have several. We have like bajillions and bajillions, and so it's perfectly fine to end up needing more than one hydroxide in your new compound, or fewer than one chloride, and making additional sodium chlorides. All right, let's see what's next. as we predict our products, let's look at some examples. All right, so here are some possibilities. That last one is going to take quite a bit to balance it. So the first thing I want you to do is pause the video for a moment and see if you can write the correct products for each reactant. So go ahead and pause. All right, now we'll look at the results. All right, we'll get barium phosphate, and you can see that it filled in with the balancing there. Next, let's see, you should get potassium sulfate and hydrochloric acid, and there it's going to fill in with the balancing. And then we should get silver chloride and ammonium sulfate, and we'll fill in with the balancing. And then this last one, it's not hard to figure out silver nitride and tin acetate, but then you see that it ends up requiring 12 of the silver acetate. So you have quite a few that have to happen there. All right, hopefully that went well, and you had good success on that sample. When we have double replacement, that will take place in an aqueous solution. Remember that aqueous just means that our compounds are dissolved in water, and you can tell that by seeing the AQ in parenthesis down behind the compound name. The results of our double replacement are going to be a precipitate, or a neutralization, or the formation of a gas. If both products remain soluble in water, we are not going to consider that a double replacement. We're just going to say that everything sits in the water and stays there, because it won't actually form new compounds. All the ions will just sit together in the water. And so we would say that was non-reaction, or no reaction, or non-reactive. All right, so we're going to look at a couple of practice samples for formation of a precipitate, formation of water, or formation of a gas. All right, so first we've got that's Ki. There's not, in fact, a Kl element. So potassium iodide, aqueous, and that's ionic, so it will dissociate in water, and you'll have potassium ions and iodide ions. And lead nitrate, which is also aqueous, because it also dissociates into lead ions, lead 2 in this case, and nitrate ions. So both of those are ionic compounds which will dissociate in water. And when they do, we would expect the potassium to become potassium nitrate and the lead to become lead iodide. And that indeed is what happens. And we've got this little symbol, this little arrow, that's showing that the lead iodide is going to drop out of solution. Rather than a down arrow, I would prefer that you put the parenthesis S for solid, and that will indicate that it becomes a solid and falls out of solution, rather than the arrow. All right. The question that you're going to ask is, how did we know that would precipitate out of solution? And the answer is, we're going to look at our solubility table. You should already have that there in front of you, and I'm not going to go through it right now, but just when you look at chlorine, bromine, and iodine, you see that iodine is soluble except when it's paired with silver or lead or mercury. And so in this case it's paired with lead, and that lets us know it will be insoluble. Sodium hydroxide, which is a strong base, it will dissociate easily, and so will hydrogen chloride, hydrochloric acid, and that will dissociate as well. And of course we see that we have a base and an acid, and so we know what that's going to be, a neutralization reaction, which will result in water, H2O, and then NaCl, which is table salt and also just a salt in general. And sure enough, there you have it. And they're showing you that H2O really is bonded HOH. So each hydrogen is on the opposite side of the oxygen, and it doesn't actually form a line like it's shown in that little tan box. It actually forms kind of a boomerang shape. It's called a bent shape, and we'll talk more about why another day. You can see that the H2O is, you can't have H2O be aqueous because you can't dissolve water in water. So it's now H2O liquid and NaCl aqueous, which is dissolved in the liquid water. All right, HCl, once again, a strong acid, and K2S, potassium sulfide. Once again, two ionic compounds, both of which are aqueous and will be soluble in water. And when we look at this, we will see that this forms hydrogen sulfide gas, and is released from the reaction and bubbles out. So all of these are types of double replacement reactions where we have the typical switching. All right, let's see. Once again, formation of water in a neutralization reaction between an acid and a base, and produces an ionic compound and water. And we talked about that, so we'll quickly zip through and just let you, if you want to pause and practice balancing these, you may. Predict your product and balance. Predict your product. Oh, that's all. Neutralization reactions, and there we have it. All right, this is where we're going to do a little bit of learning today. Anytime you have a double replacement reaction that is not a neutralization, you should look and see if that produces a precipitate. In other words, if one of the products is insoluble. Of course, if both of them are soluble, then it will not react. It will be a non-reaction. So we look at our solubility chart, and we see, again, this was the one that we looked at earlier with potassium iodide and lead nitrate. And when you look, so take a moment and look at your solubility chart and look at the 1, 2, 3, 4, 5th box down, and you see that is where it mentions chlorine, bromine, and iodide, and the fact that iodine is, and then you look in that is in the soluble compounds, but if you look to the right at the exceptions box, you see that lead iodide is going to be an exception, and so it will precipitate out and form a solid, and that is then a double replacement reaction with a precipitate. Let's look at our next one, K2S, potassium sulfide, aqueous, once again an ionic compound, iron nitrate and iron 2 nitrate, which is aqueous, dissolved in water. We know that those can both dissolve in water because if I look, I'm going to look about the 6th box down and see that nitrates are always soluble, so lead nitrate will be soluble. And then I'm also going to look and see at the very top in the 1st box that the group 1 ions are always soluble unless they are in an exception that we come to later. But your group 1 ions are almost always soluble. And so sodium is a group 1 ion, potassium. Why do I keep wanting to call that sodium? I don't know. So potassium sulfide is soluble because it's a group 1 ion. Iron nitrate is soluble because it's a nitrate, and so both of those will be soluble. Then we need to look and see, okay, if we make the double switch, will one of those become a precipitate? And when I look, I can see that if I look at my insoluble compounds, I see that sulfides are insoluble. At the very, very bottom of the page, it says sulfides are insoluble unless it is with a group 1 ion or ammonium. Well, up here at the top, or in the reactant side, it was with a group 1 ion. Not anymore. Now the sulfide is with iron 2, and so that is going to form a precipitate and fall out of solution and make a nice solid. Our nitrates are still soluble, and so are our group 1 ions. and so that will definitely be a soluble compound, and so it will be aqueous. This will be solid. All right, and so that is exactly how we know which product is the precipitate, by looking at our solubility chart. All right, we're going to do a little more practice with that. We use the solubility chart, which we've been talking about. All right, and this is the same example that we've already looked at. And you find that nitrates are always soluble, and you find that iodine is soluble except when it's with lead. So there's a written explanation of what we've already talked about. Our next example, which was on the previous page also, remember that nitrates are always soluble and group 1 ions are always soluble, but when we switch, then our sulfide is not soluble unless it's with a group 1. So sulfide is insoluble unless it's with a group 1, check, soluble. Nitrates are always soluble, so we'll put our aqueous there. On the products, nitrates are always soluble, aqueous there. And sulfides are insoluble with iron, and so it forms a precipitate. Not all double replacement reactions will occur. The only time it will occur is if both products are soluble, or excuse me, it will not occur if both products are soluble. It will only occur if both reactants are soluble and only one product is. Again, that's a slight exception if it forms the neutralization with water, and or if it forms a soluble with a gas. But again, the gas is not actually, the gas will form and then release from the water. So in this case, we have a non-reaction. Can you figure out why? All right, well, first I'm going to check and see if these are both soluble. Well, potassium is a group 1 ion, so Ki is definitely soluble. NaNO3, nitrates are soluble, so both of those are soluble. But then if I look at my swap there, I see that potassium nitrate, both a group 1 and a nitrate, would still be soluble. And sodium iodide, remember that your iodides are soluble unless they're with silver, lead, or mercury. So it turns out that this will be considered a non-reaction because everything just stays in the water. It's like everything gets in the swimming pool and just splashes around and stays there. There's no reaction that takes place. Everything's just swimming around, having a lovely time. All right, so let's do a little bit of practice. We'd like you to predict the products and identify the precipitate and balance the equation. All right, I'll ask you to pause the video and complete the products and complete the products, identify the precipitate, and balance the equation for each of these. Go ahead and pause the video now and do that. Remember, if you're not practicing, then you are not planning to be successful later. In fact, you're planning to be non-successful. Pause the video and do the practice. All right, let's take a look at our answers. Lead sulfate and acetic acid. Acetic acid is aqueous, and lead sulfide is, I think I said sulfate earlier, lead sulfide is a precipitate. In this case, calcium, let's see, I think that's permanganate. I need to double check. And magnesium hydroxide. But your magnesium hydroxide, your hydroxides are not soluble with magnesium. All right, silver chloride. Silver is mostly not soluble. Well, it is not soluble with the chlorides or with the other halogens. And then we have sodium nitrate. Nitrates are soluble. So we have our aqueous and our precipitate. and sodium nitrate. Again, the nitrates are soluble. Calcium phosphate. The phosphates generally are not soluble unless it's with a group 1 ion or ammonium. All right, hopefully you had good success on that practice, and there will be more to come later. Let's talk just for a moment about combustion reactions. Combustion reactions happen when we burn a hydrocarbon. A hydrocarbon is something like butane, propane, it's natural gas, gasoline. Lots of these things that we burn for fuel are actually hydrocarbons. And so when we burn them with oxygen, we get a large release of energy. So now the trouble is you can't react them completely without oxygen. And so oxygen does not burn, but it supports combustion. And so you have to have oxygen present in order for combustion to take place, but oxygen itself does not actually burn. All right, so our hydrocarbon plus our oxygen always forms carbon dioxide and water, and then we simply balance our equations. Let's see. So there is methane and oxygen, and we balance it. And we've done practice with these before, so I'm going to move rather quickly through this. In this case, you have octane, which is found in gasoline. Octane meaning 8 carbons in single bonds, and so that's when you hear the word octane, that's what it actually means. When you hear high octane gasolines, it means you have more of this in the gasoline. And it, makes its way into your gasoline engine. I want you to see again what an oxygen intense operation this is. For every 2 molecules or 2 moles of octane, you need 25 moles or 25 molecules of oxygen, depending on if you're looking at this as molecules or moles. It's good either way. And you produce quite a bit of carbon dioxide and water, but you have just got to have a ton of oxygen to burn things, especially the longer your carbon chain gets. Now, what if you don't have enough oxygen? Then we go into something called incomplete combustion. I'm not going to ask you to predict necessarily which of that would occur, but I'll tell you that is dangerous. And when it happens, if the flame is burning orange rather than blue, then that is taking place. If you have a gas heater or a gas stove or a gas grill, if any of those are burning orange rather than blue, you have incomplete combustion taking place, and you should get that adjusted or get it cleaned or clean it yourself. Because when you do not have enough oxygen taking place, or if something else is being burned as well, you still end up with your carbon dioxide and water, but you also then will get plain carbon, which is just messy soot. That's just the black powder that forms on things. But then you get carbon monoxide, which is actually highly dangerous. It turns out that it bonds to the red blood cells and to the it turns out that it bonds to the red blood cells more strongly than oxygen does. So it actually will displace oxygen and bond and occupy your red blood cells and keep oxygen from being transported by them. And so you actually can suffocate while you're breathing if you're breathing in carbon monoxide. Very dangerous. And of course, then if sulfur and nitrogen were involved, which happens if high sulfur diesel fuel or high sulfur coal is burned, or high nitrogen coal, then you can get sulfuric acid or nitric acid produced, and that is actually part of where acid rain comes from. Is from the burning of coal that is high in sulfur or nitrogen as well. All right, just a quick balancing tip. Always start with a 1 for the hydrocarbon. And since we have oxygen here with a 2, you know that this is going to have to take place in an even number, because we can't multiply that and get an odd number. So start with a 1 and then balance your carbons, and then see what that does to your hydrogens and your oxygens. In this case, putting a 1 there and putting a 1, that's going to make a 6 carbons. So if we put a 6 here, then that gives Well, what we've got here is 1 times 6 hydrogens. So if I put a 3 here to balance out my 6 hydrogens, that's going to produce 3 oxygens, which is going to produce an odd number. So I already know that that is not going to work. So I'm going to erase those, and I'm going to double everything. I'm going to move this up to a 2. And when I move that up to a 2, that means 2 times 6 is now 12, so I'll have to put a 12 over here. Now 2 times 6 is going to be 12 hydrogens, so let's put a 6 here. That's going to generate 6 oxygens, which will go with my other 24 oxygens for a total of 30, and so we'll need to put 15 here. So when you have an even number of oxygens coming from your water, that lets you know that that is going to be a point that you can work with, unless there's some other oxygens in the, like if there were an alcohol that were being combusted, if there were some additional oxygens in the reaction. But just for a general combustion reaction, start with a 1, see what that does for your oxygens here, and then adjust accordingly. If it's an odd number, then erase your 1s and go up to a 2. All right, and there's my 15 to finish that off. All right, so 2, 15, 12, 6 is my coefficient answer. All right, here's some additional practice for hydrocarbons. Again, we've already had a lot of combustion practice, so I'll let you pause the video if you like, but I'll go through this pretty quickly. There we go. And then for a challenge question, choose some ethyl alcohol, which is an alcohol and gives you an OH. It will also burn and produce CO2 and H2O, but you've got an oxygen in with this, which makes balancing a little tricky. You just have to watch for your oxygens in more than one place. So I will leave that with you as a challenge question. Pause and predict and balance. And there we go, CO2 and H2O, and you get your coefficients listed there as well. All right, that is going to be all of our introduction for double replacement and solubility. If you want to continue with chemical reactions, we'll have an additional video for that.